Starting Chapter 3 on Variability. The first part of Chapter 3, we dealt with location. We looked at the mean, the median, and the mode, the central tendency measures. Then we looked at percentiles and quartiles as ones that are not necessarily in the middle. And we looked at the weighted mean. But now we're going to start looking at the way that the numbers are scattered out inside a data set, the variability aspect. So we're moving from location to dispersion or variability. Now we have several different measures of variability that we're going to examine. Some of them are fairly simple, like the range, and then some of them are fairly complicated, like the covariance and the correlation coefficient. The standard deviation isn't something that's really that simple to calculate, but it's something that's really useful, so it's important that you know how to calculate it. The variance, you need to be able to get that to get your standard deviation. There's another measure referred to as the variation that you calculate to come up with the variance. The interquartile range is pretty simple. It's just the difference between the third and the first quartiles. And then we're going to look at a graph called a box and whisker plot that's built from the 5-number summary. The min, the max, the median, and the first and the third quartiles. We're also going to deal with the coefficient of variation, which is useful for comparing multiple data sets in terms of their variability. And z-scores are used fairly prevalently. We're going to look at the way that you calculate them based on sample information. When we get into Chapter 6, we're going to look at what's called the standard normal variable, which is also called the z. Now the range is probably the simplest measure of variability. All it amounts to is the difference between the maximum value and the minimum value in a data set. So in this example we have the apartment rents, and they've been sorted from the smallest value to the largest value. The largest value is 715 and the smallest value is 525. So the range is how far it is basically from one side to the other. So you take the 715 minus the 525 and come up with 190. Whereas the range tells you how far it is across the entire data set, the interquartile range tells you how far it is across the middle 50%. The first quartile, a fourth of the values are less than or equal to it. The third quartile, 3/4 of the values are less than or equal to it. What you do is you figure out what the position is, and then you can get the value. Now if we use the percentile approach to get our quartiles, the first quartile would be the 25th percentile. So you would take the number 25 and you could multiply it times n plus 1 over 100. Now n in this case is 70. So we'd have 71 over 100, and we'd be multiplying that times 25. And you come up with 17 3/4. So the value of the first quartile is going to be between the numbers in position 17 and 18 when you put them in order. Now it happens in this case that the number in position 17 and 18 is the same. It's 545. So that's the value of the first quartile. Likewise, to get the value of the third quartile, first you figure out the position, which turns out to be 53 1/4, and you look for the number at position 53, and you look for the number in position 54, and you go 1/4 of the way between them. Well, once again, the numbers are the same. So the value of the third quartile is just going to be 625. But the difference between 625 and 545 is 80. So that's the interquartile range. The distance over the middle 50% of data is 80. Now there's a graphical representation that shows the variability in a set of data that's called a box and whisker plot, or it's called a Boxplot. And it's based on 5 numbers: the minimum value, the first quartile, which we just found was 545, the median, the third quartile, which we just found was 625, and the maximum. Now to calculate the range, you have to find the min and the max. The minimum value was 525 and the maximum value was 715. The only other number that you need is the median, and that's going to be halfway through the data set. It's the same thing as the 50th percentile. So you're going to find that at location 35.5. It's going to be halfway between the one in position 35 and the one in position 36. And when you look at the data set, you can see that that number is 575. Now I used the scattergram, or the scatter diagram charting capability in Excel to generate this box plot, or this box and whisker plot. The box is created by the quartiles. The left hand side of the box is the first quartile. The right hand side of the box is the third quartile. But the box represents the middle 50%. So the difference between the right hand side of the box and the left hand side of the box would be your interquartile range. The line that's in the middle of the box, sometimes it's a plus sign, sometimes it's a dash line. People use different conventions for this. But whatever the symbol is that's showing up in the middle, doesn't necessarily have to be in the middle, but just somewhere in the interior of the box is where the median is. Half the values are less than or equal to that, and half the values are greater than or equal to that. Then protruding from the box are the whiskers. The whisker on the left hand side goes down to the minimum value. The whisker on the right hand side goes out to the maximum value. But you just need those 5 numbers to construct the box and whisker plot. But it gives you an idea about how the data values, how they're scattered around. In this case, the shape of this data set, it's right skewed. There are a few large values that are going to end up pulling the mean to the right of the median. Now we've looked at the range, we've looked at the interquartile range, we've looked at a graphical representation where the box is the interquartile range. But arguably, the most widely used measure of variability is the standard deviation. But to get to the standard deviation, you have to go through the variance. The variance uses all the data. It's not just the largest value and the smallest value. It's not just the first quartile and the third quartile. You use all the data when you calculate the variance. And since the standard deviation is derived from the variance, you're using all the data to figure out the standard deviation. But it's based on the deviations from the mean. You look at the difference between the value and the mean when you go through and do this calculation. When you want to compare variability between different data sets, you can take the standard deviation, which is derived from the variance, and then you can come up with a measure called the coefficient of variation that's useful in comparing multiple data sets. Now usually when you calculate a measure for a sample, the formula is the same as it is for a population. The variance is an exception to that general rule. When you figure out the variance for a sample, you take the sum of the squares of the deviations from the mean and you divide it by n minus 1. However, when you calculate the variance of a population, which is called a parameter, you take the sum of the squares of the deviations from the mean but you divide it by the number of items in the population. Now, the little symbol that's squared is the Greek letter sigma when you do it for a population. So it's called sigma squared. We just use the letter S, which is the first letter in sigma, to represent the standard deviation. And the variance is the square of the standard deviation. So it's just called S squared. But you take the sum of the squares of the deviations from the mean to do these calculations. But it's basically just an average. Now when you figure out the variance, all you have to do is take the square root of it, and you've got the standard deviation. Now that number represents the typical deviation from the mean. Now you might think it would be easier just to take all the deviations from the mean and just add them up and take the average. The problem with doing that is that the answer is always 0. When you sum up the deviations from the mean, you'll always get 0 as the answer. It doesn't matter whether the numbers are spread apart very, very widely or whether they're really, really packed in tight together. You're always going to get 0 for the answer. Now one way around that would be to use the absolute value function, but mathematically speaking, it doesn't work as well as the square function. The square function gets rid of the problem that the negatives and the positives balance each other out. But you could also do that with the absolute value function. When you do this sort of thing for the absolute value function, it's called the mean absolute deviation. And it does have some uses. But the standard deviation is much, much, much more widely used than what's called the MAD statistic, the mean absolute deviation. But all you have to do to get the standard deviation is take the square root of the variance. You use the letter sigma, the Greek letter sigma for the population, and then it's S for the sample. But it's always going to be the square root of the variance. But how do you get that variance? All right. Now we're going to take a small example. We're not going to use the example with the 70 apartment rents in it. We're going to use a small example to show the calculations that you go through to come up with the standard deviation. So our example, we have a sample of 7. The data represents the number of years that a company was in business. Now we're going to figure out what the standard deviation is, and the symbol for that's S. So you get it from the variance. Now the variance, you take the sum of the squares of the deviations from the mean. So first you have to figure out what the mean is. Now since we're doing this for a sample, once we figure out what that number is, we're going to be divided by n minus 1. So to get the mean, we take the 7 numbers and we add them up. We get 63 for the sum, and then the sum divided by the number of values gives you the mean. So the mean turns out to be 9. Now we're after the sum of the squares of the deviations from the mean. So the column that's next to the X column is the deviation column. You take the value and you subtract the mean. You take the value and you subtract the mean. That's called the deviation from the mean. Now each one of those individual deviations has to be squared. The deviations themselves will always add up to 0. But when you square them, that's not going to be true anymore unless all the values were the same. If all the values were the same, then the mean would be the same number and all the differences would be 0. But when you square the deviations and add all the squares up, we get 152. That's the numerator in the calculation for the variance. Now this is for the sample, so we divide by n minus 1. If we were figuring out what sigma squared was, if this was a population, we would divide by the capital N. But here we have 7 numbers. 7 minus 1 is 6. So 152 divided by 6 is the variance. Now, to derive the standard deviation from the variance, all you have to do is take the square root. So you take the square root of 25 1/3, the little bar that's across the 3 means that that digit repeats forever. It's 0.333333 forever. And it's approximately 5.033 is the value of the standard deviation. Now, if you have a calculator, it doesn't take that long to hit the square root key. With a calculator, it doesn't take that long to divide by n-1. The time-consuming part of this process is figuring out the sum of the squares of the deviations from the mean. Now, that quantity I refer to as the variation, and I use the symbol SS to represent it because it's a sum of squares. But that's the part that takes the most time. Now, this shows how to do it based on the definition, but that's not the only way to do this calculation. It looks like the video creating program has kind of rearranged my PowerPoint. Without the subscript, should be inside the box. But what this slide is showing is that you can take the sum of the squares of the deviations from the mean, and you can do that same calculation a different way. You can just go through there and algebraically manipulate it. You can get the same number if you take the sum of the squares and subtract the square of the sum divided by the sample size. Now, the last thing you want to do is subtract. But this formula is useful sometimes if you know what the sum of the values are and what the sum of the squares of the values are. Then you don't have to go through there and subtract and get all those differences. Looks like for this program I'm going to have to make my boxes a little bigger. Excel has functions built into it for calculating these things. The var.s function will get you the variance for the sample, and the stdev.s function will get you the standard deviation for the sample. Inside the parentheses, you just give it the formula for the range of the data that's in Excel. Ordinarily, you use the colon operator. You give it the cell where it starts, colon, give it the cell where it ends, and that's the range. Now, you don't want to take the variance for one set of data and directly compare it to the variance for a different set of data. Likewise, you don't want to do that comparison on the standard deviations. If you have different units, you're going to get wildly different values. I used to have an example where I took some items and I figured out what the price was in Mexican pesos, and there was like 13.4 pesos to the dollar, and you figure out what the price is in dollars, and because the peso numbers are so much bigger, your standard deviation is just a whole lot bigger than it is for the values in the dollars, when really it's the same thing. It's the price for the same items. The coefficient of variation makes the adjustment for that. You take the standard deviation, and when you divide it by the mean, you're eliminating the units. It doesn't make any difference what the units are. Now you have a unitless measure. And usually you see this as a percentage, so people will multiply it times 100 and express it as a percentage. Now, the way you want to interpret this ordinarily is if it's larger, it's more variable. So if you have a data set where the coefficient of variation is, say, 20, and you have another data set where the coefficient of variation is 15, well, the one that's 20 is more variable. But it's just a way that you can take into consideration the fact that you might have different units, and this is a unitless measure. And so you can compare literally apples and oranges with this thing. This slide shows some of those calculations for the apartment rents data set. When you figure out the variance, it was 2,996.1, and I think that 6 just repeated itself, 6666 forever. When you take the square root of that, that'll get you the standard deviation, and it was approximately 54.74. And then the coefficient of variation, you take the standard deviation and divide it by the mean. The mean of the data set was 590.8. So it works out that when you compare the size of the standard deviation to the mean, it's a little bit more than 9% the size of the mean. But that's a unitless measure. So you can compare it to another data set even though the units aren't the same. Now this slide shows the Excel formulas being used to calculate these measures. The rent values themselves, they start in B2 and they go all the way down to B71. Now this slide doesn't show what's in row 8 and what's in row 9 and so forth. It just shows what's in B2 through B7. But the function itself is going to operate on the values from B2 to B71. And all you have to do is put a colon in between those two cells to get it to access all of those numbers. So the mean, the function is just called average. So you're taking the average of the cell values B2 through B71. And the median's operating on the same range. The mode, here we're using the single version. There's another mode that's what they refer to as an array formula. You have to hold down the control key and the shift key and hit enter when you want to do one of those array formulas, but it'll give you multiple modes if there's multiple modes in your data set. var.s will give you the sample variance. That's going to divide by n-1. If you use var.p, p stands for population, and it'll divide by the number of elements rather than n-1. Same thing for stdev.s and stdev.p. The .s version is for the sample and the .p version is for the population. Now the last item, the c.v. is the coefficient of variation. E6 contains the standard deviation. E2 contains the mean. You take the standard deviation, the number that's in E6, and you divide it by the number that's in E2 and multiply it times 100, and now you've got the percentage representation of the coefficient of variation. Now anytime you do one of these formulas, you start it with the equal sign. If you don't put the equal sign in there, Excel just treats it like a character string. But the equal sign means it's going to try to do a calculation. Now this slide has the values that those formulas are going to return. When you apply the average function to B2 through B71, it returns the value of 590.8. When you apply the median function to B2 through B71, it returns the value of 575. The 550 is the mode. 2,996.16 is the value for the variance. Square root of that would be the standard deviation. And then the 9.27 is the coefficient of variation. When you take the standard deviation and divide it by the mean, and then move it over 2 decimal places. Now z-scores can be used to help you identify values that are referred to as statistical outliers, or just outliers for short. When you figure out what the z-value is, if it turns out to be less than -3, or if it's more than a +3, it is way, way out there. All you have to do to calculate it is just to take the value in your data set, subtract the mean, which is the deviation from the mean, and then divide it by the value of the standard deviation. Now the formula here is showing doing this for a sample. X bar is the mean of a sample. S is a symbol for the standard deviation of the sample. You get the same formula if you do it for a population. It's just you use mu for the mean, the Greek letter mu for the mean, and the sigma, the lowercase sigma, for the standard deviation. Now when we get into chapter 6, we're going to calculate something that's called the standard normal distribution. And in chapter 6, the formula is going to be x minus mu divided by sigma. And it's the same formula. What the number tells you is how many standard deviation units is this value away from the mean. If it's a negative number, then this number is that far below the mean. If it's a positive z-value, then this is how far it is above the mean. But you're converting it from units to standard deviation units. Now there are a few problems that deal with two quantitative variables where the values are paired together, and they go through and they illustrate how to calculate something called the covariance, and then there's also the correlation coefficient. They put a subscript of x when you want to get the standard deviation for x. They use a subscript of y when you want to get the standard deviation of y. But when it's covariance or correlation coefficient, it's a mixture of the two. You're looking at the relationship between x and y. So I'm going to use the Panthers football team example. That was the one where we had the scatter diagram. It was looking at the interceptions against the points scored. Is there a relationship between those two items? But I'm going to use that example to illustrate the calculations. And this is, standard deviation's lengthy. Covariance adds a little bit more to it. So this is the data set that we're going to use. We're going to get the covariance, and we're also going to get the correlation coefficient. Now, one interception in one game corresponded to 14 points scored. In another game, there was one interception that corresponded to 17 points scored. There were two games with 3 interceptions. In one of those games, 24 points was scored, and the other game, 30 points was scored. Then there was a game that had 2 interceptions, and in that game, 18 points were scored. But the x values are the interceptions, and the y values are the number of points scored. Now we're going to figure out the covariance. We're going to look at how these things interact with each other. When you graph it and look at the graph, there was a positive relationship indicated by these numbers. Is this a mess or what? Looks like some of it didn't get converted at all. I don't know why that little question marks. Looks like it doesn't like the symbol for the mean, and looks like it doesn't like even the standard deviation symbol. Now that's strange. It doesn't do it for the x, but it does do it for the y. It's probably a spacing issue. But the first thing you do is you calculate the means. So we get the mean for the number of interceptions, and that turns out to be 2. And then you can figure out what the deviations are from the mean. Just take the value and subtract the 2. And then you can square those deviations and come up with the sum of the squares of the deviations from the mean. So for the number of interceptions for the x variable, it turns out to be 4, and there are 5 pairs of xy values. So n minus 1 is going to be 4. So the variance turns out to be 1, which is really nice, because the standard deviation will be the same thing. It's just the square root of that. So the standard deviation for the number of interceptions is 1. Then over on the right hand side, you do that same process for the number of points scored. You figure out what the deviations are from the mean, and then you square those numbers, and then add up the squares to get the sum of the squares of the deviations from the mean. And that works out to be 163.2. Now when we divide that by n minus 1, which is 4, n's equal to 5, there are 5 pairs, we get 40.8. Now when you take the square root of 40.8, you get the 6.3875 approximately. that's the standard deviation of the y values. So it's just the same old standard deviation calculation. It's just you have two variables, so you have to do it 2 times. Now the covariance is the new thing. You take the deviation of x from its mean and you multiply it times the deviation of y from its mean. So the first x value is a 1. The deviation from the mean is a -1. The first y value is 14. The deviation from the mean, the 20.6, is a -6.6. So in the middle is where we're multiplying the two deviations together. You've got a -1 times a -6.6, which gives you a +6.6. But for each one of the 5 pairs, you multiply the deviation of x from its mean times the deviation of y from its mean. And you add up those numbers. And the sum of those numbers divided by n-1 is called the covariance. So the sum of the products of the deviations from the mean turns out to be 23 for this particular set of data. Now when you divide that by 4, you get 5.75. Now when you take the covariance and you divide it by the products of the standard deviations, you take the standard deviation of x, you multiply it times the standard deviation of y. But when you take the covariance and divide it by the product of the standard deviations, that's called the correlation coefficient. Now that number has to be between -1 and +1. It cannot possibly be outside of that range. You've done some incorrect calculation if you get a number outside of that range. The closer it is to +1, the stronger the positive relationship is. The closer it is to -1, the stronger the negative relationship is. And in this case, it turns out to be a little bit bigger than 0.9. So that's evidence of a fairly solid positive relationship. Of course, you could just use Excel, and this just takes a matter of a few microseconds to do it with Excel. It takes longer to type in the data than it does to get the calculations done. It's the software that I'm using to come up with the video, I think, that's causing these things to come up with question marks and things like that. If you look at the slides as a PDF file, you're going to be able to see all these in the form in which they exist in the PowerPoint presentation. But the sample covariance function in Excel is just called covariance.s. There's not a correlation coefficient for the population and sample, differently. It's just CORREL to get a correlation coefficient. But these are built on arrays. An array is a list of numbers. If you put your x values in one column and then line up the x values with the y values and put the y values in an adjacent column, just enter into Excel what those ranges are. So for example, here I have 5 values. Let's say that the x values were in column A and they were in the first entry, the second entry, the third entry, the fourth, and the fifth entries. So I would do covariance.s left parenthesis A1 colon A5 comma. If I assume that the y values are in column B 1 through 5, then it would be B1 colon B5 and then the right close parenthesis. And same thing for the correlation coefficient. You just have to tell it, well, where are the x values, where are the y values, and it'll go through there and do those calculations for you, and it's not any pain. Now this concludes the variability portion of Chapter 3. The next presentation is going to get into probability. Chapters 4, 5, and 6 deal with probability. Chapter 4 is just the basic probability concepts. We'll probably use the contingency table or the cross-classification table, cross-tabulation if you will. Lots of different names for that. use that for the basic concepts. But then Chapter 5 will get into what's called a discrete probability distribution, the binomial. And then Chapter 6 is a normal, where we'll get more into these z-scores. But I'll be talking to you later.